Okay, so we have a question here, an argument perhaps, whether or not the EMU women's basketball team has a better or a worse free throw shooting accuracy than the men's basketball team. And notice this is a two-tail test, not just a two-sample, a two-tail test because it says, is there a difference? If we said, are the EMU women better at shooting free throws than the men, that would be directional and that would be a one-tailed. Or if we said, are the EMU men better or are the EMU women worse or are the EMU men worse? Anytime you have that directional word, that's a one-tailed test. But this is two-tailed, and this is fairly easy to get the data. I'm using it from a couple seasons ago, I think. So each of these data points are the average free throw percentage for the year for one of the women's basketball team's members, and each one of these is for a men. So first thing you might notice is there's a different number of women and men. Does that matter? It doesn't. The closer we have to balance, it does give us something called power, which is the ability to see a statistically significant result if there is one. You don't need to worry about that too much, but do know that it doesn't really matter if they're exactly the same. There is a special type of test called a matched pairs test, where you take like a pre-test and a post-test on everyone in your sample. And in that case, you do need to have the exact same number. But for a two samples test, like we're going to be talking about, it doesn't matter if they're exactly the same number or even quite a bit different. It doesn't matter. We can still run the statistics. It might just not be as powerful of a test. So here's the results. Let's go through it. Null hypothesis is that if we would take the women's average, free throw shooting average, minus the men's for all the men's, not just for this particular season, but we're using this season to represent other ones, which whether or not this one season represents other seasons, that's questionable, but it's more relevant of data, so we're using it. So if they were exactly the same and we'd subtract them, we would get 0. So the null hypothesis is there is no difference. The EMU women's average, EMU men's average, exactly the same. The alternative is that it's not equal. It could be the men's are better, it could be the women's are better, but one of the teams is better than the other. We're going to use a 0.05 alpha level of significance, two tails, like I said, and we don't worry about this here. So we had 14 women, 17 men. Here was the average for the women, 63.44% and 64.73% for the men's. Now, be careful. We can't just say, oh, look, we have the sample means and the men's was clearly higher, so we do have evidence that EMU men's basketball players in general have a higher free throw percentage than the women do. We can't do that because remember, we have to try to figure out whether or not this difference we're seeing is just due to random variation because maybe this particular season the men were a little higher than the women, or if it's strong enough of a difference in between the two that we can say pretty conclusively that there is a difference. So we jump down here to the difference between sample means, and we could get that if we this is just the women's mean minus the men's mean. So it's negative. What that means is the women's team, on average, were 1.29 percentage points lower than the men's percentage points. And the t-statistic, let's skip that. The p-value, 0.085. Remember, p-value low, null must go. How low does it have to be? It has to be under that alpha level there. And it's nowhere near that alpha level. So 0.85, we're not even close to statistical significance here. So even though the sample mean was a little lower for the women, based on the data we have, it's really, we don't really know. We don't have evidence here. We don't have convincing evidence that there's any difference between the women's and the men's team in terms of free throw shooting percentage. It doesn't mean we've proved that it's the same. We just failed to reject. In other words, we don't have good evidence that there is a difference. The confidence interval shows you a little bit about how uncertain we are. We're 95% confident that the women's average is somewhere between 15 points below the men's average and 12 or 13 points above. So it could be that the women have quite a bit higher free throw shooting percentage. We just don't have enough data or evidence in our two samples that there is a difference. And if there is a difference, we don't know in which direction it might be. Now let me show you something. If the p-value were, let's say, much closer to 0.05, let's give the women some extra points here. So let's go, let's say this person got a 100 there, and that takes us down a little bit. Maybe, ooh, this 20 here, let's say they were shooting up at a 95, and this 44 right here was also up at a 95%. Notice the p-value keeps dropping. As we increase the women's score, the p-value keeps dropping. And now we're actually, okay, we're doing the p-value in the other direction, right? That the women's is higher than the men's free throw. Let's keep doing that, and I'll show you why we're doing that. Okay, let's stop right there. If these had been our results, what could we have concluded? Well, look at the women's sample mean. They're on average shooting 77%. The men are about 65%. So pretty substantial difference, 12, 13 percentage points difference. Our p-value is 0.06. So we still say that we failed to reject the null. This has to be below 0.05 in order to reject the null. So this would not be statistically significant results. However, as you might see, common sense might tell you, this 0.06 is really not much different than a 0.04. So this is part of the problem of a cut and dry decision, like you're either statistically significant or you're not. Really here, we're on the borderline. We're not statistically significant, but we're right on the borderline. And we'll also notice that our effect size here is pretty strong. Like I said, 0.5 is medium effect or so. 0.8 standard deviations apart is a strong one in general. So here we're fairly strong on effect size, even though it wasn't statistically significant. We would say it's practically significant. And what that tells me is that our sample sizes are probably a little too small. I would maybe want to conduct more data anytime I see a potential for large practical significance, even if it's just borderline not statistically significant. I would want to collect more data, because the more data you collect, the more your statistical significance, your p-value tends to drop, especially if there's any difference at all. And so right here we could tell, yeah, the women could be up to a point lower, but they could also be up to 26 points higher. And you can see here that the bulk of the confidence interval would be that the true average between the women's and men's is that the women's is probably higher, and probably quite a bit higher than the men's based on this confidence interval.